Right. Good morning. Sorry, I'm a little behind today, but it's okay. This is our question and answer period anyway, so questions, you can ask them now. All right, so we're gonna look at these two reactions down here. Let me cut them and put them on a different page. We're gonna walk them down. And then we're gonna also start looking at the reactions on this reaction wheel also. All right, so let's take this reaction right here. This is an example of a halohydrin formation. All right, and so it's a halohydrin because the halo is for halogen. So you're gonna add a halogen, and then a hydrogen is for water, right? You're not really adding water, you really end up adding OH. And so for this, the product looks like this, right? So this is the halo part. And then this is the hydrogen part, right? So halohydrin. So, all right, sorry about that. It is a halo alcohol, let's call it that, as a functional group. All right. So with that being said, the reason why we're doing this now is because it follows the exact same mechanism of the halogenation. All right. So there's an intermediate. Let me just put this. The same mechanism. Is halogenation. Right. What that means is that when I treat the alkene with Br2, I'm going to get this bromonium ion intermediate. Just like we got with when we did the halogenation up top. So same intermediate. The difference now is that, okay, so I would have a Br minus out here, but I also have water. All right, and let me put as a side product here, plus HBr. Right, so I have the bromonium ion intermediate, and then I have, now it can get attacked by water or bromine. Right, but the fact that you're doing this reaction, excuse me, in water, there's a lot more water present than bromine, right? So water is going to act as your nucleophile in this case, and it's going to attack and pop that ring open. right? So when that happens, I end up with another intermediate. All right. Questions about that part? So the intermediate, the reason I didn't go through that first step is because we've seen that already, right? We know how that works based on the halogenation. It's the exact same process. The alkene is the nucleophile. It's going to attack the halogen, and then you get this carbocation that cyclizes to give you this chlorinium, in this case, chloronium ion intermediate. But the halogen is there in a 3-membered ring with the 2 carbons of the alkene. All right. And then again, so that's going to be the same. That part is identical. The only difference is when the ring, when that intermediate, bromonium in this case, gets attacked, is getting attacked by a different nucleophile other than bromine. Otherwise, this would just be a bromination, right? Or halogenation. But since water is more prevalent, right, there's more of it because it's actually serving as the solvent too. It's going to win out as the nucleophile. Right, so it's more abundant, so it's gonna just so since the water is more abundant, it's gonna attack. You still may get some of the dibromide, but you're gonna get more of this compound. All right. Now, what do I need to do to that in order to get to the product? To make that water simply an alcohol.
Is the other bromine gonna attack the hydrogen?
Yes. What's that process called? We learned that a long time ago. You're right. I have it.
Is it proton transfer or is it something else?
Simple proton transfer. So this is coming in like that. And then those electrons are going back to oxygen. Right, so that's how I'm going to get my product. Where this is OH, and this is Br. Come on, Russell. This is plus HBr. Right, so that's the halohydrogen. The way you know it's a halohydrogen and not just a halogen is the presence of water. Right, when you see bromine and water together in the reactions sequence, then you know that it's halohydrogen and not just halogenation. If you just see bromine by itself or chlorine or iodine by itself, then you know that it's a halogenation. But the reason I did it together is because they follow the same mechanism up until the point of the ring opening.
I remember for like halogenation, like we talked about trans in the state.
This is going to follow the same pattern too. It's going to be trans as well.
Okay.
Yep. Because the intermediate is the same type of intermediate, right? Where bromine is here, right? So it's either going to be, both of those lines are going to be wedged and coming out of the paper or out of the screen, or they're both going to be dashed and going into the screen, right? So that doesn't change. So the stereochemistry is still going to be trans as well. I'm glad you said that. So still have trans stereochemistry. Good observation. All right. The other reaction here is also a halohydrin. It's just with different reagents. So NBS and DMSO and water. NBS is a similar type of reagent. It looks like this. So it's a 5-member ring with a nitrogen. It has a bromine attached to nitrogen, and then like so. So NBS is N bromo. Succinimide. All right, so this is my bromine source. All right, so that's where my bromine is going to come from, but the outcome is the same. Even if it's a different set of reagents, the outcome is still going to be the same. I'm going to have a alcohol on one side and a bromine on the other side. Right, that doesn't change the outcome. It's just a different set of reagents. So that's the purpose of making flashcards. If you see this set of reagents, then you know it's also a halohydrin synthesis.
So halogenation is without the water. correct?
Yes.
Okay.
If you see water present with the halogen, then it's and you reacting that with the alkene, a double bond, then it's a halohydrin synthesis, right? Those are your, I hate to say ingredients, your reactants. I'm not gonna say ingredients because then you might liken this to cooking, but it's not. So your reactants for all of these reagents, we're talking about reactions of alkenes. So you're gonna start with a double bond. And depending on what you reacted with, that's going to determine the product. So for halohydrin synthesis, I need an alkene, a halogen, and water. Right. And then here also, let me point this out. DMSO is a solvent. Right. It doesn't react. Right. That's your solvent along with water. Right. It's a highly, and let me just give you this dimethyl sulfoxide. It looks like this. So S. Right, it's a really polar solvent. So DMSO and water, that's your solvent system. NBS is your bromine source. And those are also reagents for halohydrin synthesis. All right, we won't go through the mechanism for that. You just need to know that those reagents in the presence of an alkene are going to give you a halohydrin. All right, any questions about that? All right, we're going to come back to the other set of questions up here to ask about the alkene starting material. Right, you can kind of see it says what alkene can be used to prepare each alkyl halide as the exclusive product of an addition reaction. So all that's asking you to do is to eliminate. That's how you would get back to the alkene, right? Because if you add to the alkene, you're breaking it. If you eliminate from it, then you're going to reform the pi bond, right? So that's what that's asking. So we're going to come back and do that later, because I don't want to get bogged down with that, because we've already kind of talked about elimination. It's just a matter of figuring out where the leaving group is and then finding the alpha protons. But we'll come back to that. I want to do more with the reactions. So let's go down to here. All right. So this, don't let this wheel intimidate you. It looks like a lot, but it's the same. We just got a bunch of reactions on here that we're gonna work through. So between today and Friday, we're gonna probably work through all of these. This stuff here, this will just be like kind of a review, the last part. But let's go back, let's go to here, right? And then I want to categorize these reactions. There's a little bit of a lag with my Wi-Fi. I'm not sure why, but let me. All right, so we're going to categorize these reactions. So the first reaction, we're going to just start here at 9 o'clock. So the first reaction is osmolation. And then this reaction right here is oxymercuration. They both have a similar outcome, right? So let me give you all right, so there's a subset of reactions that we can use to convert alkenes into alcohols. All right. So again, an alkene is your double bond. That's going to be your main star material for all of these reactions, because that's what we're doing. We're looking at reactions of alkenes. But then the products, you can convert alkenes into a lot of different types of products. So here, we're going to look at these two reactions. They convert alkenes into alcohol. So for alcohols, we basically have two reactions that we're going to look at. One is going to be, sorry about that, oxymercuration. Just shrink that down. So oxymercuration, and then the second one is going to be hydroboration. And I know this sounds like a lot, but it'll all make sense when we look at the actual reagents. So hydroboration followed by oxidation. But then another type of alcohol is a diol. It's just a alcohol that has two OH groups instead of just one. So for diols, we're going to look at osmolation. All right, so osmolation. So over here, these are the reagents for osmolation. Right, you have osmium tetroxide. And sodium hydrogen sulfide. Right, those are your two sets of reagents. Right, let me show you the outcome first, and then we can talk about the the mechanism, not in great detail, but I'll give you a general idea of what happens in the mechanism. Right, so for this is a way to make diols from alkenes. Right, so if you're making a flashcard for this particular reaction, that's what's on the front of the card. Right, that these are the reagents for diol synthesis. And I'm gonna show you here. So we have a fire member ring like that. And then the diol itself, anytime you do osmolation, both OH groups end up on the same face. Right? So it's a syn addition of a diol. And that methyl group that was here, because the alcohol is pointed up and they're on the same carbon, the default position is going to be, sorry about that, to be pointed back into the page. Right? So on any given carbon, right, there are two positions like that. If you're looking at it in skeletal form, one is going to be wedged and the other one is going to be dashed. Right, so if the wedge position is occupied by some other atom, then the other position by default is going to be dashed. Right, so this diol is what we call a syn diol, right? Because the OHs are on the same, or cis. Right? Those terms are synonymous when you're talking about stereochemistry. So syn or cis, you can kind of interchange them. All right. So with the osmolation, that's what I get. That's my product, right? So the reason why we see that is because there's an intermediate that looks like this. So here's my ring. And I'm gonna make this stay true to what I had. This is here, and this is here, and this is O, and this is OS, and O, like so, right? So you get right. So this is the CH3 right here. So this osmate intermediate this is where that product is going to come from, because that's like the first step in the reaction is for osmium and the alkene, right, to interact with one another. And then the second step, the sodium hydrogen sulfide, is used to break that up. So break up the osmate intermediate and also reoxidize it, because keep in mind, these oxygens that are here stay, right? Because obviously they stay because you have a diol in the product. So the second step in the reaction is to break that intermediate up and release your diol, right? Questions about that? So anytime you see an alkene in the presence of osmium tetroxide and then sodium hydrogen sulfide, you're going to get a diol, right? And just to be 100% candid, the two alcohols, they can be up or back. It doesn't matter, because there's nothing to favor one over the other. Not here anyway.
You said you have to, I guess in the intermediate, you need to break it up. So I guess how would the arrows go?
For the intermediate part right here, you mean with the sodium hydrogen sulfide?
Yes.
Yeah, so that is a little bit beyond the scope of the class, but it's kind of, how do I put it? There's some debate on whether or not it's a radical process or whether or not it's a polar process.
Okay.
But I can show you after class. 'Cause I
Okay.
don't want to get too deep in the weeds with that particular mechanism, but I can definitely show you after class.
Okay. So we just know the osmium is just gonna, I guess, disappear from that.
Yes,
Okay.
yeah, but I'll show you. I can show you after class. All right. All right, what about this reaction? We don't even have to. So this is something that we've already done. If I add HCl to that alkene, what am I going to get?
Alkyl Halo.
Okay. What side in that alkene is the halogen going to end up? Where's it going to go?
I think it's on the most substituted because it's Markovanov rule.
Markovnikov, good. Yeah, and the hydrogen from the HCl is going to go here on the least substituted side. You're right. This is addition of HX, and it is Markovnikov. All right.
Can you show how it's, I guess, more substituted? I get confused on that part too.
All right, can you see here on this side of the, so this is the alkene right here. Right, this side has hydrogen, it has a carbon here, and the other side has 2 carbons. You're looking at each carbon in the alkene separately.
So on the left side, you have 2.
Mhm.
Okay.
You see the ones I have like here and here? Got
Yeah.
a carbon here and a carbon here, and on the other side, you only have 1 carbon there. And the other substituent is hydrogen.
Okay.
All right. So that we've done that reaction already. So that's why I'm not going through the mechanism again or anything like that. We're just predicting the products. What about here? What reaction is that? And what's the outcome?
Would that be one of the ones we just went over?
Yes, sir. It's a halogen synthesis. Is that right?
Yeah.
So what is the outcome? Right? It is a halogen in this case is bromine.
And then an OH?
Mhm. And then the OH is going to be here. So I'm going to write that like this. The bromine is going to be here. And the reason I'm showing the stereochemistry is because it's trans, just like it would be if it was a halogenation. Right. And then the methyl group, I'm going to draw that here. Like so. So this is a halohydrogen. Right. Questions about that? Because that one, we just did that and everybody's quiet. Except Eli. So any questions about that? Again, when you see an alkene in the presence of bromine and water, or chlorine and water, or iodine and water, it can be any halogen except fluorine. When you see that set of reagents in the presence of an alkene, it's got to click automatically that that's going to be a halohydrogen synthesis.
I have a question.
Go ahead.
Where did the stage 3 come from?
right here.
Oh, okay, okay.
All right, so it's only 2 new reactions on here. And we can talk about them both. Let's start here because this is the easiest one out of the 2. So this is a hydrogenation. Hold up. All right, so you can see the reagents, H2 and a platinum catalyst. All right, it's either platinum or palladium. And this is a pretty involved mechanism too. But I'll be happy to do this, like show the arrows and all that stuff afterwards. But the outcome of the reaction is very simple. This is a way to convert alkenes into alkanes. What's an alkane? Anybody?
Single chain.
Yeah, all single bonds. All right. So what I'm doing in this particular case is I'm adding a hydrogen to either side of the, and I'll give you a generic mechanism. But I'm adding a hydrogen to both sides. I'm gonna change the color on those hydrogens. Right, so I added a hydrogen to both sides. That's what that does, right? I take hydrogen gas and either platinum oxide or palladium on a solid carbon support. Right, this is what happens. So let me give you, I'll give you a rough way of how this happens. So here's my alkene. I'm gonna just draw it like that. And then if I just do this with platinum oxide, right, what I get is a platinum complex that has hydrogens attached like so, right? So it goes through a couple of different steps in this particular mechanism, but at the end of the day, so the platinum is going to coordinate to your alkene, and then it's going to transfer both hydrogens. One is coming here, and then the platinum ends up on one carbon in that alkene. So let me show you that. So I've added hydrogen here, and then I also now have platinum with another hydrogen on it. Right now, just put some ligands out, just generic ligands. Right, so that's that part. This part is called insertion. Right, so the platinum actually gets added. You actually get a covalent bond between platinum and carbon. And then the next step, you get elimination, reductive elimination. And that's going to give you this. And it's going to put that other hydrogen out here. And then it's going to regenerate your platinum catalyst. So this is going to come here like that. And this is, again, kind of beyond the scope of the class, but it's good to know. So your platinum catalyst gets regenerated. Always, anytime you use a catalyst, that's going to be regenerated in the end.
Does that say,
Platinum. Go ahead.
does that say PT platinum L2?
Yeah, because like it's not just platinum, like it does, platinum doesn't just, well, it does exist, but when you use it as a catalyst, more than likely it's going to have something attached to it, some type of ligand attached to it. In this case, I think it's platinum oxide, so it's PTO2. So it's got two oxygens attached to it. But again, I'm trying to keep this as generic as possible, just so we can get the gist of what's happening.
I have a question.
Go ahead.
You said that was called reductive elimination.
Yeah, so the first step is insertion, and then the second step is reductive elimination. All right. So yeah, so if you take an alkene and treat it with hydrogen gas in the presence of a catalyst like platinum or palladium, if you watch the alkenes video, one of the reactions in there was the hydrogenation reaction. I think I sent that already. I may not have, but I'll send it today. Because there's another type of catalyst you could use. This palladium, and it's similar. It's like, but it's on a solid carbon support, and it's with the same mechanism. So that's the hydrogenation. We've looked at osmolation. We've already looked at addition of HX. The last reaction, we got 2 minutes left. I'll show you the outcome, and then we'll talk about the mechanism on Wednesday. And I'm gonna show you the other reaction that is kind of parallel to this, but with different regiochemistry. So with this reaction right here, this is a way to convert alkenes into alcohols, right? And this is oxymercuration. Right, and I think the last video I sent had that and the mechanism in there. But the outcome is, and this is a reaction, if you boil it down, it's like adding H to one side and OH to the other side. So it's like kind of adding water to the double bond, right? The difference is for this is Markovnikov. So the OH from, and this is very generic. We'll talk about the mechanism Wednesday. But the OH is going to add to the more substituted side. All right, so it's going to end up on that side where that CH3 is. So let me just show you the product, and then we're going to stop, and then we'll pick up on Wednesday. So the OH ends up here. Right, and what I want you to notice, all of these products, at the end of the reaction, the double bond no longer exists. And that's one of the reason I say that is because that's a common mistake that I've seen year after year as I teach this section, is that students will somehow forget that once you use up the electrons in the alkene, the double bond is not going to be there anymore in the product. So don't forget about that. Like, notice here, there's no double bond left. I've added something to it, and so those electrons got used up. Right, so I'm gonna stop here. This is the product. Notice where the OH is on the more substituted carbon. And then so when we come back on Wednesday, we'll pick this up and I'll show you a different reaction. And hopefully you've already watched that video. We're gonna talk about this reaction right here first, because this is the hydroboration oxidation reaction, which is parallel to oxymercuration, but instead of being Markovnikov, it's anti-Markovnikov. So we'll talk about that on Wednesday. All right, any questions? And then we'll go through the mechanisms for both. All right, if no questions, then we're gonna stop here. Let me stop recording first.